I'm Chris Brotherton. I'm a professor of atmospheric science at the University of Washington. I'm one of the co-PIs of CSET. And my main role in this project is at the interface between modeling and the observations we're taking of cloud, aerosol, precipitation interaction. And one of the important features of CSET is that we are using Lagrangian sampling, meaning that we're trying to sample air masses as they evolve. And one of the nice things about studying the boundary layer is that the air is actually mixing up. So throughout the entire depth of the boundary layer, the air is churning away, and so the entire air mass moves as a single column as it flows downstream. So what we can do is we can use trajectories of boundary layer air that we determined from a numerical model, and Hans will talk about that, to then track boundary layer air masses, and then we can see how they evolve. And so we have an example here from our current research flight pair, RFO2 and RFO3. So these stars here indicate air that we sampled during RFO2, so that was on the 7th of July. And you can see the cloud features that they sampled as well. So there's a kind of a big hammerhead here of bright cloud, and then there's a region of more broken cloud to the west, and then there's some sort of cloud bands further to the west of that. So now if we take a look at what happens over the course of time, here are our trajectories a day later. So the black points are now the new locations of where we sampled originally along these. And so you can see that, so now we're a day later. We're not actually sampling this air with the aircraft. This is while our plane was sitting in Hawaii, but you can see here are the new locations of the air. And you can see some of the same cloud features as you can the previous day. So here's the hammerhead feature. And if you sort of compare with the previous day, you'll see that the cloud features are kind of drifting along with the wind. That if you go back to this, here's the hammerhead. The bottom of the hammerhead is below the sampling points. And over here is the advected location of the sampling points here, 2, 3, and 4, and there's the hammerhead just below them. And then if you go one day later to today when we sampled again, now things are getting a bit more distorted and the colors changed. But the west end of that sampling is here, and it's now coincident with the south end of the hammerhead. So the cloud features are sort of drifting along with the wind, and this means that this is a better way to look at the evolution of the boundary layer is following this moving air mass. Everything that happens in this air mass will then, we don't need to worry about things blowing in and blowing out of it. Everything that's happening is happening internally to that air mass, and so it's easier to understand our results that way. And we can look at some other features too here. Actually look at some features off on the west end of the trajectory. Here it's a little bit harder to see the features, but here are sort of 3 long linear features in the first day, and here they are on the second day, and they were sort of off to the northwest of the sampling points here. Here they're sort of more off to the west, but they're still sort of off to the northwest here. So again, the features are kind of blowing along with the wind. Now, one issue that we have is that our trajectories are actually coming from winds from a forecast model. We don't know if they're even right. So we can actually use the motion of cloud features to tell us if our trajectories are reasonable. Now, so how do we use this? Well, so what we are going to do is we're going to look at models too. So we can look at global models, or we can look at process models that we use to understand these clouds. For global models, we'll just sample the model of the position of these moving air parcels and see how the clouds look compared to our results and how the aerosols look. For process models, we run a very fine resolution large eddy simulation model. So it's a model on a grid which might be 50 meters or less in the horizontal, 10 meters or less in the vertical. And we run it over sort of a 10 by 10 kilometer region of ocean and air above it, column of air above it. And then what we do is we move this column of air following the motion where the wind's blowing. So we're going to use the same conditions that this real air column experiences to try and simulate its evolution as it feels the changing sea surface temperature and upper level conditions, and see how well we can simulate the cloud and air assumption.